Over the next hour, I'm going to take you on an immersive journey to see just how hard it is for aliens to find Earth. If there really are no aliens in the universe, is that actually a good thing for us or a bad one? You can go ahead and like this, save it, and play it in the background. Find a comfortable position, and get ready to drift off to sleep. Right now, you're lying in bed, most likely in the middle of a city. Most likely, there are lights all around you. If you turn all the lights off, and pull back the curtains, if you're lucky, you might see a few dozen stars. If you're unlucky, you won't see a single one. Just the AC units on the building across the street. But if you were in a place with zero light pollution, like the Qinghai Tibet Plateau, or right in the middle of the Sahara Desert, or on a little boat in the Pacific with no lights at all, looking up, you'd see about 5,000 to 8,000 stars. The Milky Way looks like a glowing river, stretching across the entire sky. You'd feel like there are just too many stars to ever count. Now, let me give you a number. There are roughly 200 billion to 400 billion stars in the Milky Way. Those few thousand you see with your naked eye are only 0.000 something percent of the galaxy. In the entire observable universe, there are about 2 trillion galaxies. Each galaxy has an average of 100 billion stars. If you multiply it all together, the total number of stars is about 10 to the 24th power. That's a 1 followed by 24 zeros. This number is many times larger than the total count of every grain of sand on every beach on Earth, with so many stars out there. And the universe being 13.8 billion years old, statistically speaking, even if the chance of life appearing is ridiculously small. With a sample size this massive, it stands to reason that the universe should be teeming with civilizations. But what do we actually see? Absolutely nothing. No signals, no spaceships, no ruins. There isn't a single shred of evidence suggesting that apart from us, any other intelligent civilization has ever existed. The universe is despairingly vast and dizzyingly old, yet it's as quiet as an empty house. Humanity has been seriously searching for alien signals for over 60 years. Back in 1960, Frank used a radio telescope in West Virginia to point at 2 nearby stars, Tau Ceti and Epsilon Eridani. They listened for months, but didn't pick up a thing. Since then, the SETI project has used ever larger telescopes, ever more sensitive receivers, and increasingly clever signal processing algorithms. They've been searching for decades. The Arecibo Observatory, the Green Bank Telescope, the Breakthrough Listen project, hundreds of millions of dollars have been poured in, along with the careers of countless scientists, and the result is zero. Every now and then, there's been an anomalous signal that made our hearts skip a beat. Most famously the WOW signal from 1977, a strong signal that lasted for 72 seconds, but it never appeared again. After over 60 years of searching, with thousands of stars carefully scanned, the universe has responded with nothing but silence. Tonight, let's take our time and talk about 2 things. Just how hard is it for aliens to find us? And if they don't exist at all, what that means for humanity? And if you happen to get sleepy while listening, that's perfect, because it illustrates just how hard it is to find your address in the cosmos. Let's start by getting a sense of just how difficult it really is to find Earth. First, you have to know where Earth is, the location of the solar system within the Milky Way. It's 26,000 light-years away from the center of the galaxy. Sitting right on a spiral arm called the Orion Arm, the Milky Way is about 100,000 to 180,000 light-years across. So, where does the Sun rank in the Milky Way? Honestly, it's basically just a nobody. Not too big, not too small, not too bright, not too dim. Within the Milky Way, G-type stars like our Sun, there are probably tens of billions of them. Trying to pick out the Sun from those tens of billions, it's just like trying to find one specific person in all of China. Someone with average looks, average height, and an average age, and you don't even know their name. Then, you have to know that the Earth revolves around the Sun. The Sun has 8 planets. Pluto has already been kicked out of the club. Earth is the 3rd one counting from the inside out. If you look at the solar system from a few hundred, even a few thousand light-years away, what can you actually see? Basically, you can only see the Sun. The planets are just too small and too dim. The Sun's light completely drowns them out. To put it into perspective, imagine you are standing in Beijing. Trying to see a firefly next to a lighthouse in Shanghai. The lighthouse is 1 billion times brighter than that firefly. You would have to block out the lighthouse's light perfectly, just to catch a glimpse of that firefly. That, fundamentally, is the difficulty of observing exoplanets from afar. The methods humans currently use to find exoplanets mainly rely on two techniques. One is the transit method. When a planet passes in front of its star, it blocks a tiny bit of the star's light. The star's brightness drops by an incredibly small amount. The Kepler Space Telescope used this very method to find thousands of exoplanets. But this method has one critical, make or break requirement. The planet's orbital plane must be perfectly aligned with your line of sight. If the angle is off by even a tiny bit, the planet won't pass in front of its star. And you won't see a thing. For a planet like Earth, which is 1 astronomical unit away from its star, the probability of being observed is only about 0.5%. In other words, even if there were 200 suns in the galaxy, for an Earth-like system, on average, only one would be at the perfect angle for you to see. Another method is the radial velocity method. A planet's gravity causes its star to wobble ever so slightly. About 9 centimeters per second. 9 centimeters per second. Imagine you're tens of light years away, trying to measure a stellar speed change of 9 centimeters per second. That level of precision, even the best equipment humans have today, can only just barely reach it. So, for an alien civilization to find Earth, even just to discover a planet next to our sun, that first step alone requires incredibly precise astronomical equipment and an incredibly lucky viewing angle. And that's just the easiest step. Let me help you grasp the difficulty in another way. Imagine you are an alien astronomer living on the other side of the galaxy. Your civilization is very advanced. You have a massive space telescope. You want to find every potentially habitable planet in the galaxy. The galaxy has about 200 billion to 400 billion stars. You look at them one by one. Suppose your telescope can analyze 1 star per second. Spectral analysis, planetary detection, and habitability assessment. Doing the whole process perfectly. 1 star per second for 200 billion stars. It would take you about 6,300 years just to finish looking. And for every single star, you need luck. Is the angle right? Is the planet passing by at the perfect moment? Is the signal strong enough? Finding a needle in a haystack doesn't even come close. It's more like being in the middle of the Sahara Desert, looking for a specific grain of sand. And you don't even know what that grain of sand looks like. If you were to write out the Earth's full cosmic address, it would look something like this. Laniakea Supercluster. Virgo Supercluster, Local Group. Milky Way Galaxy, Orion Arm. Local Bubble, Gould Belt, Solar System, third planet from the Sun. Every single layer is just a tiny speck within a much larger structure. When you look at it from the scale of the outermost supercluster, the Milky Way is just a faint, tiny point of light. At the scale of the Milky Way, the Sun is just one unremarkable star, among hundreds of billions of others. At the scale of the solar system, Earth is nothing more than an invisible speck of dust next to the Sun. Layer upon layer of sheer insignificance. And even if you found it, so what? How would you know if there's life on it? Let's say some alien civilization has discovered the solar system. They've also spotted, right next to the Sun, a rocky planet of just the right size. Then what? How would they know there's life on that planet? The most they could probably do is analyze the spectrum of Earth's atmosphere. When sunlight passes through Earth's atmosphere and heads out into space, the various gases in the atmosphere leave their unique signatures on the light spectrum. These absorption lines are just like a fingerprint. Oxygen has its own fingerprint. Methane has its own fingerprint. And ozone has its own fingerprint. There is 21% oxygen in Earth's atmosphere, which is absolutely unique in the entire solar system. Oxygen is an incredibly reactive gas. It's constantly desperate to bond with everything else. That's why iron rusts. And wood burns. If there wasn't a constant, ongoing replenishment, the oxygen in our atmosphere would be completely absorbed by the rocks and the oceans within a few million years. The only reason Earth's atmosphere can maintain such high levels of oxygen is that something is constantly producing it. That something is photosynthetic plants and cyanobacteria. So, if an alien civilization could detect large amounts of oxygen in Earth's atmosphere, they could reasonably infer that there is some kind of biochemical activity on this planet, continuously generating oxygen. But the question is, can you, from tens of light years away, or even hundreds of light years away, detect the atmospheric composition of a planet? Theoretically, yes. When a planet transits its star, the star's light passes through the edge of the planet's atmosphere. The molecules in the atmosphere leave a fingerprint on the spectrum. The James Webb Space Telescope is already doing exactly that. It has already detected the atmospheric composition of some hot Jupiters. But hot Jupiters are much larger and much closer to their stars. For a small, rocky planet like Earth, that is far from its star. The atmospheric spectral signal is so weak it's almost drowned out by noise. And even if you do detect oxygen, you can't be 100% sure it was produced by life. Theoretically, certain non-biological processes could also cause oxygen to accumulate on a planet. For example, ultraviolet light can break down water vapor, a process called photolysis, producing hydrogen and oxygen. Hydrogen is too light and escapes into space, while the oxygen remains behind. Early Venus may have gone through this very process. So, a cautious alien scientist, upon seeing oxygen in Earth's atmosphere, might write in a paper that biological activity is a possibility. But they wouldn't slam the table and claim they've found alien life. The real smoking gun would be detecting both oxygen and methane simultaneously. Methane is also an unstable gas. In an atmosphere with plenty of oxygen, methane would be oxidized, and would be completely consumed within a few hundred years. In Earth's atmosphere, the presence of both high concentrations of oxygen and significant amounts of methane suggests that something is constantly producing these two contradictory gases at the same time. On Earth, oxygen comes from photosynthesis, and methane comes from microorganisms, primarily methanogens in the stomachs of ruminants, and anaerobic bacteria in wetlands. This thermodynamically unstable atmospheric combination is, according to all known non-biological chemistry, almost impossible to maintain spontaneously. If an alien astronomer were to detect that a planet's atmosphere contains both oxygen and methane, they could basically pop the champagne. But take note, from dozens or hundreds of light years away, precisely measuring the concentrations of these two trace gases in the atmosphere of a small rocky planet requires a level of telescope precision, at least an order of magnitude higher than the best equipment humanity currently possesses. For us, it will probably be the latter half of this century before we can possibly achieve this. For an alien civilization to do the same, they would also need extremely advanced technology. The James Webb Space Telescope, since it began operations in 2022, has indeed already begun analyzing the atmospheric composition of some exoplanets. It detected carbon dioxide and sulfur dioxide in the atmosphere of the exoplanet WASP-39b. WASP-39b is a hot Jupiter, a massive gaseous planet orbiting very close to its star, which has a much thicker atmosphere and a much stronger signal. For small, rocky planets like Earth, Webb's sensitivity is still not enough. Next-generation telescopes, such as the planned Habitable Worlds Observatory, might be able to do it, but that's a task for the 2040s or even later. There is a fascinating thought experiment. Suppose there is an alien civilization on the other side of the Milky Way. Their telescope technology is 10,000 years ahead of ours. They aim their sights toward the sun. They discover Earth. They analyze Earth's atmosphere. What would they see? It depends on which version of Earth they are looking at. The speed of light is limited, which means you are always seeing Earth as it was in the past. If they are 26,000 light-years away from us, on the other side of the galaxy, they are seeing Earth as it was 26,000 years ago. Back then, Homo sapiens already existed, but there was no agriculture. There were no cities. There was no industry. The atmospheric composition was almost identical to today's. It had oxygen and methane. Because these are maintained by the biosphere, they have nothing to do with civilization. They would know there is life on Earth, but they wouldn't know there is a civilization. Even if they used the most advanced equipment, the Earth they see is still 26,000 years younger than the one we are on now. On that Earth, your ancestors were painting on the walls of some cave. This is another layer of isolation brought by the speed of light. It is not just spatial isolation. There is also temporal isolation. Anything you see in the distance is just how it looked in the past. You will never be able to see the present of a distant celestial body. Perhaps at this very moment, a civilization is looking toward the solar system. But what they are seeing is Earth as it was thousands of years ago. Perhaps thousands of years ago, a civilization took a glance at our solar system. They saw a blue planet with oxygen, but no signals of civilization. So, they filed it away as a boring planet with just microbes. And then they moved on to look at something else. By the time our radio signals reach them, they might already be gone. Missed, gone forever. Let's say, even if we know there is life, do you know if there is a civilization? Alright, let's assume an alien astronomer, using their incredibly advanced telescope, confirms there is life on Earth. But life does not equal civilization. Earth has had life for nearly 4 billion years. But an intelligent civilization has only existed for a few thousand. Throughout the vast majority of Earth's history, over 99.99% of it, if you were to look at Earth from far away, all you would see is just a planet with blue-green algae and single-celled organisms. No cities, no lights, no radio signals. Just a lush, green, quiet ball. How would aliens determine that Earth doesn't just have bacteria, but also a civilization? The most obvious answer is radio. Ever since Marconi invented the radio in 1895, humanity has been leaking electromagnetic waves into space. Radio, television, radar, cell phone signals. These signals spread in all directions at the speed of light. That's been going on for about 130 years. So, in theory, within a spherical region, with Earth at the center and a radius of 130 light-years, it's possible to receive Earth's radio signals. A radius of 130 light-years covers about a few thousand stars. That sounds like a lot, but the Milky Way has hundreds of billions. Our signal is like a single cup of water, poured into the Pacific Ocean. Its volume is so small it's basically negligible. And there is an ironic trend in all of this. As technology advances, Earth is actually becoming quieter and quieter. Early radio and television signals were broadcast using high-power, omnidirectional antennas. A huge amount of energy leaked into space. But nowadays, communications are increasingly shifting to fiber optics and low-power, directional digital signals. These hardly leak into space at all. Satellite communications use narrow beams, aimed directly at ground receiving stations, so they don't just scatter everywhere. In other words, the brightness of Earth in the radio spectrum has likely already started to fade over the past few decades. In another 100 years, Earth might just look like any other planet without a civilization in the radio spectrum. Quiet. We inadvertently opened a window. And now we're closing it again. But there is a practical issue here. Signal attenuation. The strength of a radio signal is inversely proportional to the square of the distance. A signal sent out from a broadcast station, by the time it reaches a few light years away, is already too weak to be detected. Even with something like the Arecibo radio telescope, that kind of high-power directional radar, those pulses, that famous 1974 transmission aimed at the M13 globular cluster. By the time it reached the nearest star, Proxima Centauri, 4.24 light-years away, signal density was already so weak that you'd need a receiving antenna, much larger than Arecibo, just to pick it up. By the time it hits 7,100 light-years away, it's basically just buried in the cosmic background noise. What about Earth's lights? Looking at Earth's night side from space, you can definitely see the city lights. But that's from low Earth orbit, just a few hundred kilometers away. If you look at Earth from the distance of Pluto, it's just a pale blue dot. In 1990, the famous pale blue dot photo taken by Voyager 1 shows exactly that. You can't see the city lights at all. From several light-years away, looking at Earth, it's just an invisible speck of dust next to the sun. There's another line of thinking: industrial pollution. Human industrial activity has released massive amounts of freon into the atmosphere. The refrigerant for refrigerators and air conditioners that's now been banned, and other synthetic chemicals. These substances do not exist in the natural world. If you were to detect chlorofluorocarbons in a planet's atmosphere, it would be almost certain to be the product of an industrial civilization. But the concentration is far too low. In Earth's atmosphere, the concentration of freon is only a few parts per trillion. From dozens of light-years away, detecting this level of concentration would require a space telescope with a diameter of perhaps over 100 kilometers, at least for the foreseeable future. No civilization is capable of doing that. Therefore, the conclusion is, even if an alien civilization confirmed that there was life on Earth, they would still find it very difficult to determine whether this planet has an industrial civilization. From their perspective, Earth and a planet with only bacteria are almost indistinguishable. We think we are quite conspicuous. We've built cities, constructed rockets, and broadcasted radio waves, but on a cosmic scale, the visibility of these things is practically zero. We are, in this universe, a tiny existence so quiet that we are nearly invisible. On February 14, 1990, after Voyager 1 flew past Neptune's orbit, it received a command from NASA to turn its camera around and take a photograph of Earth. At that moment, Voyager 1 was about 6 billion kilometers from Earth, approximately 40 astronomical units away. In that photograph, what did the Earth look like? It was a pale blue dot that took up less than a single pixel, hanging in a beam of sunlight. When Carl Sagan saw this photograph, he said something, the gist of which was, "Look at that dot. That is here. That is home, that is us. Everyone you've ever known. Everyone you've ever heard of. Every human being who ever lived out their lives on that little dot. 6 billion kilometers, not even one light day away. Light day is about 26 billion kilometers. Viewed from this close, the Earth is just a tiny dot, barely visible. And what about from dozens of light years away? Non-existent, completely non-existent. The sun's brilliance just drowns everything out. We humans have a very naive intuition, feeling that our civilization is grand and conspicuous. We've reshaped the surface of the Earth, lit up our cities, filled up near-Earth orbit with satellites. But this sense of scale and prominence is only relative to the Earth itself. Compared to the solar system, our presence is completely negligible. Compared to the Milky Way, even the presence of the solar system is negligible. We are, like bacteria living on the surface of a single grain of sand, thinking we've transformed the entire grain, and that the whole desert should take notice. But the desert doesn't know. There are trillions of grains of sand in the desert. You transformed one. Nobody can see it. This sense of insignificance isn't meant to be depressing. It's meant to be sobering. It makes you realize that aliens haven't found us. Perhaps there's no need for any complex explanation at all. Maybe the answer is just the simplest one. They can't see us. Even if they're at the very next star. Even if their telescopes are 100 years more advanced than ours. It's highly likely they still wouldn't see us. Because we are too small, too dim, and too quiet. 4 meters from this wall. Even if aliens knew where Earth was, even if they knew there was life here, or even an advanced civilization, the idea of them actually coming here to take a look is almost impossible. The reason is simple. The distance is just too vast. The closest star, Proxima Centauri, is 4.24 light-years away. 1 light-year is about 9.46 trillion kilometers. So, 4.24 light-years is roughly 40 trillion kilometers. The fastest man-made object humanity has ever built, the Parker Solar Probe, travels at a top speed of about 200 kilometers per second. At that speed, flying to Proxima Centauri would take about 6,300 years. And keep in mind, that's just the closest one. Throughout the Milky Way, most stars are separated by distances ranging from dozens to thousands of light years. The speed of light is 300,000 kilometers per second, and it is the universal speed limit for anything that has mass. Even if you could travel at the speed of light, crossing the galaxy would still take 100,000 to 180,000 years. And according to Einstein's special theory of relativity, accelerating an object with mass to the speed of light would require an infinite amount of energy. In other words, faster than light travel is physically impossible. So what about getting close to the speed of light? Let's say, 10% of light speed, which is 30,000 kilometers per second. It would still take 42 years to reach Proxima Centauri. That's an entire generation. Sounds barely doable, right? Do you know how much energy it takes to reach 10% of light speed? For a 1,000-ton spacecraft, the kinetic energy required to hit 10% of light speed is roughly equivalent to dozens of times the entire planet's annual energy consumption. And that's just for accelerating. We haven't even factored in slowing down. Once you reach your destination, you have to spend that same amount of energy all over again to decelerate. Otherwise, you'll just go whizzing past at 10% of light speed. It flew away before I could even get a glimpse. You've probably heard of concepts like warp drives and wormholes. In theoretical physics, there are indeed solutions within general relativity, like the Alcubierre metric or Alcubierre drive, that allow for the distortion of space itself, to achieve faster than light travel. But all these proposals require something we don't even know exists yet. Exotic matter. Something with negative energy density. Currently, there is zero experimental evidence to suggest this kind of matter exists. It's the same story with wormholes. General relativity allows for them, but maintaining a traversable wormhole would require massive amounts of negative energy to hold it open. These things look beautiful written on a blackboard, but the distance to actually engineering them is likely even greater than the distance to Proxima Centauri. So, even if there is another intelligent civilization in our galaxy, and even if they know we're here, popping over for a visit would be virtually impossible. The scale of the universe turns the idea of neighbors visiting into a joke. We say the nearest star is 4 light-years away, using the word nearest. But that nearest means 40 trillion kilometers. To help you visualize that number, if the Sun were a basketball sitting in Beijing's Tiananmen Square, Earth would be a sesame seed 15 meters away. Then the nearest star, Proxima Centauri, would be another basketball, placed all the way in Hangzhou. You trying to travel from Tiananmen to Hangzhou to find a sesame seed? That's just a typical day in interstellar travel. Voyager 1, the farthest man-made object in history, was launched in 1977. It has been flying for nearly 50 years now, and is about 24 billion kilometers away from Earth. That sounds really far, but that distance, that's only about 2.5 thousandths of a light year. If you wanted to fly to the nearest star, it would take about 70,000 years. 70,000 years, 70,000 years ago, Homo sapiens were just beginning to migrate out of Africa. Even if we upgraded our technology to nuclear pulse propulsion, which is basically tossing nuclear bombs behind a spacecraft, using the shockwaves from nuclear explosions for thrust, that kind of violent aesthetic approach, theoretically, we could reach about 5% of the speed of light. It would take about 85 years to reach Proxima Centauri. That's a lot faster, but it would still take several generations. And every single push from nuclear pulse propulsion is an actual nuclear explosion. You would need to detonate tens of thousands of nuclear bombs one after another behind your ship. This concept was actually seriously discussed back in the 1950s under the American Project Orion. It was shelved because of the Partial Nuclear Test Ban Treaty. It's technically feasible, but politically completely impossible. A more elegant solution is the laser sail. You'd have a giant laser array on the ground or in space, aimed at an incredibly light and thin reflective sail. Firing lasers at it, the light pressure pushes the sail, accelerating it to break through. The Breakthrough Starshot project wants to use this method to launch tiny, gram-scale probes, accelerating them to 20% of the speed of light, reaching Proxima Centauri in about 20 years. But that can only push something weighing a few grams. To push a manned spacecraft, the laser power you would need might be equal to hundreds of times the entire planet's current power output, and you would need to keep the beam focused for years, no matter what propulsion method you use. The core difficulty of interstellar travel isn't speed, it's energy. Accelerating an object with mass to near light speed requires energy that is directly proportional to its mass. A manned spacecraft weighing several thousand tons accelerate to 10% of the speed of light, and then decelerate to a stop. The energy required is roughly equivalent to a few percent of the total energy the sun outputs in 1 second. That doesn't sound like much, but you have to concentrate all that energy into a single spacecraft. The most powerful nuclear bomb humanity has ever built, the Tsar Bomba, had an energy yield of about 200 million tons of TNT. But compared to the energy needed to accelerate a ship to 10% of the speed of light, it's basically just the equivalent of a single matchstick. 5. If the vast distances weren't despair-inducing enough, there's an even more hidden and fatal obstacle: time. The universe is 13.8 billion years old. Earth is 4.6 billion years old. Life has existed for about 4 billion years. But a technological civilization, the kind that can broadcast radio signals and build telescopes, has only existed for less than 200 years. How much of Earth's history is 200 years? About 1/20 millionth. And how much of the universe is history? About 170 millionth. Imagine you are in a pitch-black stadium, holding a laser pointer. You click it randomly, emitting a flash of light for 1 millisecond. There is someone else in the stadium, who also has a laser pointer. And they also click it randomly, for exactly 1 millisecond as well. What are the odds that both of you press your buttons in the exact same millisecond? If there were a 24-hour clock running above the stadium, the probability of you both happening to light up at the same time is about 1 in 86 million. This is the dilemma of two civilizations happening to exist during the same time window. The history of the Milky Way spans 13 billion years. The lifespan of an industrial civilization might only be a few hundred to a few tens of thousands of years. No one knows the exact number, because we are the only sample we have, and we aren't done yet. Let's hope so. If a civilization lasts for 10,000 years on average, then the window of time it appears in the history of the galaxy is like 10,000 years out of 13 billion. 1 in a million. The probability of two civilizations happening to exist at the same time is 1 in a million times 1 in a million, 1 in a trillion. Even if throughout the history of the galaxy, a total of 1 million intelligent civilizations have appeared, and that is a very generous assumption, the probability of there being two of them existing at the same time is still incredibly low. Most of the time, there are either 0 civilizations in the galaxy, or just one, a lonely civilization, that turns on its lights for a little while, and then goes out. And then, a long time later, another civilization turns on its lights in another corner for a little while, and also goes out. They will never know that the other ever existed. That is why they say time is crueler than distance. You can at least find ways to overcome distance. Build faster spaceships. Just take more time. But the misalignment of time windows is absolute. A civilization that went extinct 500 million years ago, no matter how glorious it once was, to us today, is no different than if it had never existed at all, unless they left behind some kind of relic that could last for hundreds of millions of years. But hundreds of millions of years is enough to wipe away any trace of a material civilization. Continental drift, plate subduction, meteorite bombardments, stellar evolution. After hundreds of millions of years, nothing would remain. Let me give you a picture. Imagine the galaxy is a pitch-black city, where every building represents a star. Occasionally, light turns on in one of the windows of a building. A civilization has appeared. The light flickered for just a few seconds, considering the age of the city. And then it went out. Maybe years later, a light would turn on in a different window of another building. And 2 more would go out. The lights never shine at the same time, even if you stare at this city without blinking, at any given moment. All you see is darkness, because each light stays on for such a fleeting amount of time. Human radio signals have been traveling for about 130 years. 130 light years in a galaxy over 100,000 light years across. Our signal sphere. All the radio signals that have ever escaped from Earth, the spherical region they cover, only accounts for about a few millionths of the galaxy's volume. Even if another civilization in the galaxy is listening right now, they are most likely not within our signal sphere. They have no clue that anyone is even speaking. What's even more despairing is the delay in response. Suppose 100 light years away, someone actually received Earth's signal. They would spend a year confirming it wasn't just noise, and then send a message back. Since the message travels at the speed of light, it would take 100 years to reach us. After you send your signal, you have to wait 201 years to get a reply. The person who sent the message and the one who receives it are in all likelihood not from the same generation. This isn't a conversation. This is writing a suicide note to descendants generations later. The Fermi Paradox lunch question, the summer of 1950. At the Los Alamos National Laboratory in the United States, a few physicists were having lunch in the cafeteria. Among them was Enrico Fermi, the winner of the 1938 Nobel Prize in Physics. As they were chatting away, the topic drifted to aliens. Fermi suddenly put down his fork and asked, "So, where are they?" This question later became known as the Fermi Paradox. And its logic goes like this. The Milky Way contains between 200 billion and 400 billion stars. Vast number of them host planetary systems. Our galaxy is already 13 billion years old. That is enough time for any technological civilization to expand across the entire galaxy, even using the slowest method possible, traveling at 1% the speed of light, colonizing one neighboring star system at a time, covering the whole galaxy, would only take between a few million and 10 million years. Compared to the Milky Way's age of 13 billion years, that is barely a drop in the bucket. So, as long as there has ever been even one technological civilization with a desire to expand, they should have filled every corner of the galaxy by now. Yet we don't see any signs. No signals, no megastructures, no traces of colonization, nothing at all. We have already analyzed a few reasons for this. Distances are too great, signals are too weak, or the time windows just don't align. The true power of the Fermi paradox lies elsewhere. It's not asking why we haven't received any signals. It's asking, why does the entire galaxy look completely uncolonized? Signals might fade away, but a civilization that builds megastructures everywhere wouldn't be so easy to miss. A Dyson sphere, wrapping around a star to harvest its energy, would emit a distinct radiation signature in the infrared spectrum. A civilization that terraforms planetary atmospheres would leave behind unnatural chemical traces. But we see absolutely nothing. The galaxy is pristine and clean, like an untouched, primeval forest that no one has ever stepped into. Why? There are many explanations. Some say maybe all civilizations have gone extinct. Some say perhaps they choose not to expand. Some say maybe they are deliberately hiding from us. And some say maybe we are the first ones here. We'll discuss these one by one next. But before we do, first, let's get a feel for this. Just how powerful is the Fermi paradox? Any technologically advanced civilization that has the desire to expand, even using the most conservative methods allowed by known physics, can use von Neumann probes to explore the entire galaxy in just a few million years. A von Neumann probe is a machine capable of self-replication, flies to a new star system, uses the local asteroid materials to copy itself, and then those copies fly off to the next star. The number doubles with every replication. Even if each flight takes 10,000 years, and replication takes 1,000 years after arrival, this kind of exponential growth only requires a few dozen iterations. To cover the entire galaxy, it would take about a few million years. In the 13 billion year history of the Milky Way, there has been enough time for this to happen thousands of times. The same logic applies to Dyson spheres. A hypothetical megastructure that completely or partially encloses a star to collect all of its energy. A civilization, if it develops to the stage where it needs the entire energy output of a star, a Kardashev Type II civilization, would absolutely have the incentive to build such a structure. A star enclosed by a Dyson sphere would dim or even disappear in the visible light spectrum, but would be exceptionally bright in the infrared, because after the structure absorbs the star's energy, it would re-emit it as thermal radiation. We have already searched in the infrared spectrum. We haven't found a single credible Dyson sphere candidate. With hundreds of billions of stars in the galaxy, there isn't even one Dyson sphere. This suggests that either no one is building them, or no one has lived long enough to reach the stage of building them. Perhaps everyone is dead, the Great Filter Hypothesis. This term was coined by economist Robin Hanson in 1996. It means that on the long road from dead matter to an interstellar civilization, there is one or more nearly impossible obstacles to overcome. The Great Filter. The vast majority of attempts fail when faced with the filter. Only a tiny fraction, perhaps, only one makes it through. The filter could be located anywhere. Maybe it's at the very origin of life itself. From inorganic chemistry to the first self-replicating molecule. This step might be so difficult that the vast majority of planets in the galaxy never achieve it. Perhaps it's the leap from simple life to complex life. On Earth, single-celled organisms dominated for over 2 billion years. Before the first eukaryotic cell even appeared. Maybe it's the transition from complex life to intelligence. Dinosaurs ruled the Earth for 160 million years. Yet they never evolved a civilization. Maybe it's the leap from intelligence to technology. Humans have been intelligent for tens of thousands of years. But the Industrial Revolution was only 200 years ago. Every single step could be a filter. If the filter is behind us, like the origin of life or the emergence of eukaryotic cells, and it's an incredibly rare event, then we are the lucky few who made it through. Out there in the galaxy, Maybe there are dead planets everywhere, just filled with primordial soup. No living cells. That would be good news for us. It would mean the hardest part is already behind us. But what if the filter is ahead of us? Perhaps every civilization that develops industrial technology ends up destroying itself at some point. Maybe nuclear weapons, biological warfare, uncontrollable artificial intelligence, or irreversible environmental destruction are the unavoidable path for every technological civilization. And the vast majority just don't make it through. Maybe we are currently heading straight toward that filter. The nuclear warheads we have in our possession are already enough to scorch the Earth's surface several times over. Our carbon emissions are already changing the global climate. We are currently developing artificial intelligence at an unprecedented speed. We aren't sure if we can actually control it. Perhaps throughout the entire history of the galaxy, there are countless civilizations that have developed to a stage similar to ours, only to vanish one after another. This is, within the Fermi paradox, the most chilling part of all. If the answer is that the great filter lies ahead of us, then there is an invisible blade hanging over our heads. Every civilization that reached this point failed to make it through. Why on earth would we be any different? To be specific, what are the candidates for these filters lying ahead? Nuclear war is the most obvious one. From the detonation of the first atomic bomb in 1945 until now, it has been less than 100 years. Yet the number of global nuclear warheads once reached tens of thousands. During the Cold War, there were several times when we almost pressed the button. In 1983, the Soviet early warning system falsely reported that the United States had launched nuclear missiles. The duty officer, Stanislav Petrov, chose not to report it. It turned out later to be a system malfunction. If he had made a different decision, perhaps you wouldn't be here listening to this. Perhaps nuclear annihilation is a standard feature for every civilization. Once you master atomic energy, you simultaneously master the ability to destroy yourself. Perhaps most civilizations end up using this capability within a century or two of discovering it. Climate catastrophe is another candidate. An industrial civilization reliant on fossil fuels will inevitably change the atmospheric composition of its own planet. If it changes to an irreversible tipping point, such as triggering a runaway greenhouse effect, the planet could become another Venus. Venus might just be a cautionary tale. Some scientists believe that Venus may have had liquid water and a mild climate in its early days. A runaway greenhouse effect turned it into a hellscape with a surface temperature of 460 degrees. Artificial intelligence going out of control is a relatively new candidate. If a civilization we've developed an AI that's beyond our ability to control, the outcome depends entirely on what that AI's objective function is. And in the vast majority of cases, that objective function might have absolutely nothing to do with protecting its creators. Biotech disasters are also on the list. Gene editing is becoming easier and easier, and cheaper. Perhaps every sufficiently advanced civilization eventually produces a madman, or suffers a single accident that unleashes a man-made, unstoppable pathogen. Each one of these possibilities might have a low probability on its own, but when you stack them all together, nuclear war, climate change, AI, biotechnology, and other risks we haven't even thought of yet, the total probability might not be low at all. Perhaps the chance of a civilization surviving more than 1,000 years after mastering planetary-scale power is only a few percent. If that's the case, then in the history of the Milky Way, perhaps tens of thousands of civilizations have already perished. We might be the latest one, but it's unlikely we'll be the last, unless we do something differently. Or perhaps they're hiding from us. A rather gentle explanation is called the zoo hypothesis. It was proposed by astronomer John Ball in 1973. It suggests that advanced civilizations might indeed exist in the galaxy, but they choose not to contact us. Just like how we establish nature reserves and don't interfere with the wild animals inside. Perhaps Earth is just a cosmic nature reserve, fenced off by more advanced civilizations, watching us from afar, but not interfering. This hypothesis has a certain logic to it. To a civilization millions of years ahead of us, we might just look like ants. Would you negotiate with ants? Would you teach ants calculus? At most, you'd just stand on the side and watch their anthill. That's pretty interesting, and then just walk away. Maybe that's how advanced civilizations look at us. The dark forest theory takes a different approach. It's much darker than that. This concept was popularized by Lou Sixon's novel, The Three-Body Problem. But similar ideas had been proposed long before that. The core logic is, civilizations in the universe don't know if others are friendly or hostile. Plus, communication delays between civilizations span light years. By the time you figure out their intentions, they might have already built a weapon pointed right at you. In such an environment of extreme distrust, the safest strategy is that as soon as you find another civilization, you wipe them out immediately, before they have the chance to wipe you out. That's why every intelligent civilization in the universe is desperately trying to stay hidden, not sending out any signals at all, staying silent, just like a hunter in a dark forest. Because once your location is exposed, that's the end. If the dark forest theory is true, then a lot of what humanity is doing is incredibly dangerous. Like the radio signal sent in 1974 from the Arecibo radio telescope toward the Messier 13 star cluster. Or the location of the solar system marked on the Voyager Golden Record. And the projects actively beaming messages to extraterrestrial intelligence that intentionally aim high-powered signals toward potentially habitable star systems. The universe really is a dark forest. These actions are basically lighting a campfire in the woods and shouting, "I'm over here." But the dark forest theory has its flaws, too. It assumes that destruction is safer than negotiation. But wiping out a civilization dozens of light years away requires a massive investment of resources. And how can you be sure you've actually wiped them out? They might have already spread to multiple star systems. Miss one, and you're just inviting retaliation. In that kind of scenario, building a system of trust might actually be more rational than indiscriminate extermination. But who knows? The game theory of extraterrestrial civilizations might be completely different from our own. Another possibility is that advanced civilizations do exist, but they have transcended forms of existence we can even comprehend. Perhaps they've uploaded their consciousness into a digital world, no longer needing stars or planets, no longer interested in the physical universe. They live inside computers, running on super servers deep within the core of some rogue planet, producing almost no detectable signals at all. From our perspective, they're no different from not existing. Yet they are there. It's just that their way of being is completely beyond our range of detection. Think about how eerie that is. Maybe at this very moment, there are 10,000 advanced civilizations in the galaxy. But they all live within their own virtual realities. Completely uninterested in the physical universe. They don't build Dyson spheres. Because they don't need that much energy. A nuclear reactor at the core of a small asteroid is enough to run their entire digital civilization. For billions of years, they don't broadcast signals, because there's no one they want to talk to. The virtual universes inside them are 10,000 times more spectacular than the real universe outside. They don't explore, because they don't have to. They have already simulated every corner of the galaxy within their digital worlds. To them, the real Milky Way is just a low-resolution, boring, and outdated version limited by the laws of physics. Why would they ever need to leave? If this is the answer, then the Fermi paradox isn't a question of where they are, but a question of what they are paying attention to. The answer is, they aren't paying attention. They are not paying attention to the material universe. Just like you wouldn't pay any mind to a single bacterium in the soil of your garden. It's not that you hate it. You just never even think about it. All of these hypotheses, the zoo hypothesis, the dark forest, the digital transcendence, share a common, unsettling trait. They are all unfalsifiable. You can't prove that there aren't hidden civilizations out there. You can't prove that no one is intentionally avoiding you. You can't prove that you aren't just an animal kept in a nature reserve. This unfalsifiability gives the entire discussion a flavor of philosophy, or even theology. The Fermi paradox. Perhaps there will never be a definitive answer. It might be the ultimate open question that humanity ever faces. Something you can always keep questioning, but never reach a conclusion. Unless one day, we actually receive a signal. That day, everything will change. Perhaps we really are alone. Now, let's talk about the possibility that really gives people the creeps. Maybe, in the entire universe, it really is just us. This possibility isn't something that can just be dismissed. We currently only have one known origin of life event. This one time here on Earth. We have no idea what the probability of this happening is. It could be as easy as rolling dice. Give it the right conditions and it just happens. But it could also be as rare as rolling a six-sided die. 10,000 times in a row and getting a 6 every single time, a probability close to zero. It's just that the universe is big enough that it happened to occur on one planet by chance. Think back to what we discussed, if you heard that episode. The origin of life requires that, from inorganic molecules, a self-replicating molecular system spontaneously emerges. A simple, self-replicating RNA molecule requires at least dozens of nucleotides, arranged in the exact, correct order. The probability of such a sequence occurring randomly is so infinitesimally small that calling it astronomical would be optimistic. Every form of life on Earth uses the same genetic code, the same 4 bases, and the same codon translation rules. This means success may have happened only once. Just once. 4 billion years. The chemical reactions of an entire planet succeeded only once. If the probability of life originating is truly extremely low, say, 10 to the power of -40, then even if there are 100 billion suitable planets in the Milky Way, the expected value is still far less than 1. Perhaps this has only happened once in the entire universe. We might be more than just lucky. We might have hit a jackpot, with odds smaller than all the world's lotteries combined. From prokaryotes to eukaryotes, this is yet another threshold. On Earth, single-celled prokaryotes dominated for about 2 billion years. 2 billion years, and only then did eukaryotic cells emerge. As for that event, the current mainstream explanation is that an archaeon engulfed a bacterium, but didn't digest it. That bacterium became the mitochondria. The probability of such an event might be just as absurdly low. Maybe there are bacteria on many planets in the Milky Way, but eukaryotes have never appeared. From multicellular organisms to intelligent life, at another threshold. Dinosaurs thrived on Earth for 160 million years, without developing intelligence. If 65 million years ago, that asteroid hadn't struck the Earth, and wiped out the dinosaurs, mammals might still be trembling at the feet of the dinosaurs today. Let alone evolving into Homo sapiens. The emergence of intelligent life may require a series of highly improbable, accidental events. It happens continuously. The planet has the right conditions. A stable period long enough. Just the right environmental changes to put pressure on evolution. But not so much that it leads to extinction. There is a detail in here that is particularly worth pondering. That asteroid that wiped out the dinosaurs. The Chicxulub impactor. With a diameter of about 10 to 15 kilometers. Traveling at about 20 kilometers per second. It slammed into what is now the Yucatan Peninsula in Mexico. The energy released by the impact was equivalent to 100 trillion tons of TNT. About 1 billion times that of the Hiroshima atomic bomb. It caused global wildfires and tsunamis. Years of impact. Winter dust and sulfate aerosols blocked out the sunlight. Global temperatures plummeted. Non-avian dinosaurs went completely extinct. 75% of species on Earth disappeared. But the size of this asteroid was just right. If it had been any bigger, say 50 kilometers, it might have wiped out all land-based life, including mammals. If it had been any smaller, say 3 kilometers, it might not have been destructive enough. The dinosaurs would have survived, and mammals would still be playing a supporting role. Exactly 10 kilometers, just enough to wipe out the dinosaurs. But it left the mammals behind, and just happened to give primates a chance to rise to the top. Your existence depends on the fact that 65 million years ago, a rock of the perfect size, at the perfect speed, and at the perfect angle fell from the sky. If the probability of every step above is very low, and you multiply them all together, the final probability might be so low that it only happens once in the entire observable universe. We might truly be the only ones. Think about it even more carefully. How special are the conditions of Earth itself? The distance from the star is just right. A little bit closer and it would turn into Venus. Shift a little further, and you'd get Mars. We have a massive moon, stabilizing our axis of rotation. Without that moon, Earth's climate would swing wildly, like it's gone insane. We have Jupiter out there acting as a bodyguard, catching most of the asteroids that might have smashed into Earth. We have a core of liquid iron generating a global magnetic field, blocking solar winds to protect our atmosphere, plus plate tectonics. Cycling carbon, keeping the climate stable for the long haul, plus liquid water. Plus just the right atmospheric composition. Plus the perfect rotation speed and tilt. These conditions, looking at each one individually, maybe they aren't that rare. But the probability of all of them happening at once might be so low you wouldn't even dare to calculate it. There is an extreme possibility worth thinking about in the dead of night. Perhaps the emergence of life doesn't just require the right kind of planet. It also needs the right universal physical constants. The strength of gravity, the strength of electromagnetism, the value of the strong nuclear force. They are all precisely tuned to within a window that allows for complex chemistry. Change any one of those constants even a tiny bit, and either atoms wouldn't exist, or stars wouldn't burn, or carbon, the core element of life, couldn't be synthesized. Our universe happens to sit in an incredibly narrow window of parameters. Perhaps the vast majority of universes, if a multiverse even exists, simply don't allow for any form of life to exist at all. We just happen to be in one that does. When you pile all these just-sos on top of each other, just happening to be in a universe with the right physical constants, just happening to be on a planet with the right conditions, just happening to have life spontaneously emerge from a chemical soup, just happening to have that life evolve into eukaryotic cells, just happening to have those cells develop into multicellular organisms, just happening to have an asteroid at the perfect moment wipe out the dinosaurs, clearing the way for mammals, just happening to have a certain type of primate evolved brains large enough, and by sheer coincidence they learned to use fire and make tools, farm crops and build cities, even inventing radio. If any one of those coincidences hadn't happened, you wouldn't be here tonight listening to this. Your existence right now is the endpoint of an incredibly narrow, almost impossible path. 10. If we are the only ones. Is that good news? We've finally reached the core question of the night. If we are truly all alone in the universe, is that ultimately a good thing or a bad thing? Intuitively, many people would feel it's bad news. How lonely that is. An observable universe 13.8 billion light-years across, trillions of galaxies and sextillions of stars. And we're the only civilization. The sheer scale of that loneliness is enough to take your breath away. But wait, look at it from another angle. Remember the Great Filter? If there are no aliens in the universe, then the Great Filter is almost certainly behind us, rather than in front of us. Because if the filter were in front of us, some force destined to destroy technological civilizations, lying in wait for every species that reaches our stage, then throughout the history of the galaxy, there should have been many civilizations that reached a similar level of development. But since we don't see a single trace of them, there are only two possibilities. Either they were all wiped out by a filter ahead of us. Bad news, or they never appeared in the first place, because the filter behind us was simply too difficult to pass. Good news. If there are no aliens, it's because the origin of life itself is incredibly rare. That would mean we are the lucky ones who, like a miracle, passed the hardest trial. There is no inevitable destruction waiting for us up ahead. Our future is wide open. We have the chance to become, in the Milky Way, or perhaps even the entire observable universe, the only interstellar civilization. This isn't loneliness. This is a mission. Look at it the other way around. Suppose we discover that the galaxy is teeming with microbes, but no complex life. That would actually be good news. It would mean that the origin of life isn't hard, but that the step from simple life to complex life is incredibly difficult. The Great Filter is behind us, and we've already passed it. What is the worst news? That we find the galaxy is full of complex life. Even remnants of early civilizations. No existing advanced civilizations. This means that civilizations reaching our current level must have existed many, many times. But they all perished. The Great Filter is ahead, and we will be no exception. So, the absence of aliens in itself isn't good news. Nor is it bad news. Whether it's good or bad depends on the reason. If the reason is that the starting point is too hard, congratulations, you are a miracle of the universe, and the road ahead is clear. If the reason is that the finish line is too near, sorry, you are the next one of us destined for extinction. We don't yet know which one is the reason. This uncertainty, in itself, is the kind of feeling that keeps you tossing and turning in the middle of the night. You don't know if you're a miracle, or the next sacrifice. You don't know if what lies before human civilization is an infinite sea of stars, or an invisible wall. You only know that for now, you are still here. For now, the lights are still on. This signal has not yet faded. 1961, astronomer Frank Drake wrote an equation, later known as the Drake equation, aiming to estimate how many communicable alien civilizations might exist in the Milky Way. The equation is a product of a series of probabilities. The rate of star formation in the Milky Way, multiplied by the fraction of stars with planets, multiplied by the average number of habitable planets, multiplied by the probability of life emerging, multiplied by the probability of intelligence evolving, multiplied by the probability of developing technology for communication, multiplied by the length of time a civilization survives. This equation doesn't provide an answer, because we don't know most of the variables. But he broke the problem down, letting you see clearly whether aliens exist. That big question actually consists of what smaller questions. The most interesting part is that last variable, the length of time a civilization survives. If a technological civilization only lasts a few hundred years on average before self-destructing, then even if new civilizations pop up frequently in the Milky Way, the number of them existing at the same time is very small. But if a civilization can survive for millions of years, or even billions, then in the Milky Way, there could be thousands of civilizations all at once. So, whether the absence of aliens is a good thing or a bad thing for us? The answer to this question, in a sense, depends on how we choose to live our own lives. If we can find a way to keep human civilization from going extinct, not get blown up by nuclear bombs, not get killed off by the climate, not get replaced by artificial intelligence, not get wiped out by a plague, if we can make it through all these hurdles, and live until the day we can colonize other star systems, then we will be the proof for that final variable in the Drake equation. That civilization can survive for a long time. Maybe we are the first ones to do it. And maybe we are not. It's just that the other civilizations that have made it are living too far away. We can't hear them. Regardless, we have the chance to try. This isn't just some trivial philosophical question. It might be the most important practical issue in the entire universe. Whether a civilization can survive its own adolescence. Humanity is probably right in that adolescent phase now. We have enough power in our hands to destroy ourselves, but not enough wisdom yet to make sure we won't use it. Can we grow up? Maybe the whole universe is waiting for that answer. But perhaps the answer isn't just one of two choices. I don't want you going to sleep feeling anxious. So, let's talk about another possibility. One that's more complex than just a yes or a no, but also a lot more interesting. Maybe alien life exists, but it's nothing like what we imagine. When we search for alien life, we're searching for life just like us. Carbon-based, using water as a solvent. Needing oxygen, living on the surface of rocky planets. But why should life only exist in this form? Maybe deep in the atmosphere of some gas giant. There's a self-replicating molecular system based on ammonia and silicon, using lightning as its energy source. Maybe on the surface of some neutron star, there's life made of extremely dense matter, held together by nuclear forces instead of chemical bonds, running millions of times faster than we do. Its entire life cycle might only last a few seconds. Maybe dark matter, that stuff that makes up 27% of the universe's mass. The stuff we know absolutely nothing about, has its own chemistry, its own complex structures, its own form of life. It just barely interacts with ordinary matter, so we can't detect it at all. This might sound like science fiction, but 20 years ago, the analysis of exoplanet atmospheres sounded like science fiction, too. 50 years ago, the detection of gravitational waves also sounded like science fiction. The universe has proven time and again that its imagination is far richer than our own. Perhaps, life isn't a binary issue of existence or non-existence. Perhaps it's a spectrum. From the simplest self-catalyzing chemical reaction networks, to increasingly complex self-organizing systems, to molecules capable of self-replication, to single-celled organisms to multi-celled organisms, to conscious, intelligent life, to digital entities that transcend physical form. At different points along that spectrum, there may be a variety of life-like phenomena scattered about. They might not meet our definition of life. But they aren't merely inert matter, either. The chemical universe might not be teeming with life, nor is it completely empty. Instead, in different places, and in different ways, within that gray area between living and non-living, all sorts of possibilities are being explored. Perhaps one day, we will find microorganisms in the subglacial oceans of Europa. Perhaps we will find something in the methane lakes of Titan, self-replicating system not based on DNA, Perhaps we will find a biological source of phosphine in the upper atmosphere of Venus, where the temperature and pressure are just about the same as Earth's surface. In the year 2020, scientists did announce that they had discovered phosphine in Venus's atmosphere, but subsequent verification sparked controversy. To this day, the matter remains unsettled. Each discovery of this kind, even if it's just a single-celled microorganism, will fundamentally change humanity's understanding of our place in the universe. If, within our own solar system, there were two independent origins of life, for instance, carbon-based life on Earth, and something completely different, some other chemical form of life, beneath the icy crust of Europa, that proves one thing. Life is not an accident of the universe. Life is an inclination of the universe. Given the right conditions, life will just spring up. In that case, there is almost certainly life everywhere in the galaxy. The answer to the Fermi paradox then becomes that the distances are too great, or our time windows don't align. Rather than there being no life at all, the universe isn't an empty house. It's a garden. It's just that the garden is too vast, and the flowers are too far apart. Every flower thinks it is the only one. There is another possibility, somewhere between life everywhere and only us. Perhaps simple life, at the microbial level, is very common in the universe. Complex life is extremely rare, and intelligent civilizations are so incredibly scarce that in the entire galaxy, there might only be one or two at a time. The universe might be a wilderness overgrown with moss and lichen, with a great tree popping up in some corner every once in a while. We are that great tree. Moss is everywhere. But those great trees are separated by tens of thousands of light years. This rare Earth hypothesis suggests that microbial life might only need liquid water and an energy source. Those conditions are quite common in the galaxy. But going from microbes to multicellular organisms requires a series of highly improbable leaps. And from multicellular to intelligent, it requires another series of them. Each step drastically reduces the number of candidates. In the end, those who can make it to the point of building a telescope may only number a few in the entire history of the galaxy. If that is the case, our meaning to the universe is more than just merely existing. We might be the only ones in this part of the galaxy who can perceive beauty, and who can ask questions. Why is it that looking up at the stars fills us with such awe? That's not narcissism, that's irresponsibility. If consciousness is truly this rare, then wasting it is a cosmic sin. Every brain capable of thought is a miracle condensed from 13.8 billion years of cosmic history. Treat it with kindness, the final candle, no matter what the truth may be. Whether the universe is teeming with life or we are all alone, one thing is certain. Right now, you are awake. You have consciousness. You are pondering these questions. In the entire known universe, this thing called consciousness has only ever been confirmed to exist. Within you and your billions of human companions, there is no second sample. Think about that. Perhaps consciousness, a cluster of carbon-based molecules made of stardust, being able to realize its own existence, being able to ask if there is anyone else out there in the universe, is the rarest phenomenon in the observable universe, rarer than any element, rarer than gold, than platinum, rarer than the state you are experiencing right now, where someone is watching, someone is listening, and someone is thinking. Perhaps within thousands of light years, it only exists here on Earth. If that is the case, then what you are holding in your hand isn't just a phone. What you are holding is one of the most unlikely outcomes. In 13.8 billion years of cosmic history, your consciousness is a candle burning in the darkness of the universe. Perhaps it is the only one, perhaps not, but regardless, it is burning right now. And that is enough. Perhaps one day, humanity will receive a signal from a distant galaxy, a series of rhythmic pulses, too rhythmic to be a natural phenomenon. And on that day, the history of mankind will be forever divided into before and after. Before, we thought we were alone. After, we knew we were not. On that day, the entire Earth will probably fall silent for a few seconds. Perhaps that day will never come. Perhaps the universe is just this quiet. Perhaps from the moment of the Big Bang until the very last star flickers out. 13,800,000,000 years, multiplied by who knows how many eons into the future. Conscious matter, only on a third planet. orbiting an ordinary star, flickered for just a brief moment. Tens of thousands of years, maybe millions. And then went out, leaving the universe in silence once again. No one remembers, no one knows, but you know now. At least tonight, you know. You might just be the rarest thing in the universe. You know that this experience called consciousness might be more precious than any diamond. You know that when you open your eyes tomorrow morning, the moment you see the sunlight, it could be the most incredible event currently taking place in the entire Milky Way. A lump of stardust has woken up, sees the light, feels the warmth, and remembers the story about aliens you heard last night. One day, perhaps in a few decades, or perhaps in a few centuries, one day, human probes will reach Europa. They will drill through the icy crust and lower a camera into that dark, 100-kilometer deep ocean. The moment those images are transmitted back, the whole world will hold its breath. If there's nothing there, just darkness and saltwater, it would mean that life is truly rare, and that we are all the more precious. But if something drifts in front of the lens, even if it's just a cluster of moving cells, it would be the most significant discovery in human history. More important than discovering new continents. More important than landing on the moon. Because it would answer the one question we've been asking for thousands of years. Are we alone? No matter what the answer may be, the act of asking itself is already extraordinary. In a universe 13.8 billion years old, at least one collection of molecules made of carbon, hydrogen, oxygen, and nitrogen has learned to look up at the sky and ask, is anyone out there? Perhaps someone will answer, or perhaps no one ever will. But this very question, one mass of matter asking if there is another mass of matter in the universe asking the same thing, might just be one of the most beautiful things to ever happen in the cosmos. Epilogue. Alright, it's getting late. Those questions about the Fermi paradox, the great filter, and the dark forest don't need to be answered tonight. They have already waited 13.8 billion years. They can wait through your sleep. Right now, you are on Earth, a planet sitting in the perfect position, orbiting the perfect star. It has liquid water, a magnetic field, and an atmosphere. It has a giant moon to help stabilize its axis. It has a 4 billion year history of life. There are millions of species alive on this planet, and among them, one primate that gazes up at the stars and wonders. Regardless of whether there is anyone else out there in the universe. At this very moment, this planet exists. At this moment, you exist. At this moment, your heart is beating. Your body temperature is beginning its natural nightly dip. Deep within your brain, your pineal gland is releasing melatonin into your bloodstream. Your breathing is slowing down. Your muscles are relaxing, one by one. Those muscles you used all day to fight against the pull of gravity. The soleus muscles in your calves, the quadriceps in your thighs, the erector spinae in your back, now have their job taken over by the mattress. They can rest now. Gravity is still there, but you don't have to carry it anymore. The bed is carrying it for you. That star outside your window has already turned to the other side of the Earth. It will be several hours before it returns. While it is away, cosmic microwave background radiation from 13.8 billion light-years away. The lingering warmth of the Big Bang, at a temperature of about minus 270 degrees, is blanketing the Earth, but you cannot feel it. The atmosphere wraps you up tight, and your blanket keeps you warm and snug. The tens of trillions of cells in your body are quietly performing their nightly maintenance, repairing the tissues worn down during the day, sorting through the memories of the day. Your immune system is on patrol. There is no need for you to worry. This system has been running for 4 billion years. It knows how to take care of you. Perhaps there is someone else in the universe. Or perhaps not. Maybe on some distant planet. At this very moment, there is another being, lying down and preparing to fall asleep. Wondering the same question. Is there anyone out there? If that's the case, you don't even know the other exists. Separated by tens of light years, or even hundreds of light years of vacuum, yet you're in the same universe, made of the same stardust, governed by the same laws of physics, closing your eyes on the same night. I suppose that counts as companionship. A kind of companionship that spans light years, needing no confirmation. You are not alone, even if in this universe, there really is only one kind of you. Those thinking carbon-based clusters. You still have 8 billion of your own kind beside you. More than half of them are getting ready to sleep, too. On this page of Earth, billions of people are closing their eyes right now. And you are one of them. You are all spinning on this planet together. Traveling through the universe together. Drifting together on a little boat made of stardust. Go ahead and close your eyes. Let all those thoughts about filters and paradoxes, and the speed of light and probability, slowly sink away. They'll be there waiting for you. Maybe you'll keep thinking about it tomorrow. Maybe next month. Or maybe on some summer night. When you look up at the Milky Way by the sea, you'll remember what you thought about tonight. And when you do, just watch quietly for a while. Look at those few thousand stars visible to the naked eye. And think of them. Every single one might have its own planets. Think about how those planets might have oceans, atmospheres and lightning, and some sort of chemical reaction that is currently trying to become something alive. Then take a deep breath. That breath of air is the latest serving of the oxygen that blue-green algae first began exhaling 4 billion years ago. Then slowly breathe it out. Your eyelids are growing heavier. That's the melatonin kicking in. Your pineal gland has already picked up on the signal of darkness and has started running the program it executes every single night, lowering your body temperature, slowing down your heart rate, relaxing your muscles. This is a program your ancestors have been running for hundreds of millions of years. Ever since the earliest fish crawled onto land, they've had a circadian rhythm. The sleepiness you feel right now is a 400 million year old evolutionary legacy. Trust it, the universe outside is still spinning on. The Milky Way is still moving through space at over 200 kilometers per second, carrying you along with it. The sun is still traveling at 220 kilometers per second, orbiting the center of the galaxy. And the Earth is still racing around the sun at 30 kilometers per second. You are on this spaceship traveling at over 100,000 kilometers per hour. Just lying there quietly. Everything is as it should be. Everything is just fine. Perhaps, right now, in some corner of the Milky Way, an unmanned radio telescope is pointing silently toward the sun. It belongs to a civilization that vanished long ago. The people of that civilization are long gone, but their machine is still faithfully running. Always listening, always recording. Maybe in a few thousand years, our earliest broadcast signals will reach that distant telescope. It will faithfully record them, storing them on a hard drive that no one will ever come to read. A monologue. A monologue from a little blue planet. No one will reply, but it will have been recorded. In a sense, that is enough. You are living in a universe where perhaps yours is the only civilization. The preciousness of this fact is beyond anything you can imagine. We'll cut it here. And that brings our journey to an end.